Building Blocks of Matter by Lillian Duggan. How did we learn about atoms? Structure of the atom. Charcoal and aluminum foil look different, but both are made up of atoms joined together. The carbon in charcoal and the aluminum in aluminum foil are both pure substances. The smallest whole piece of a pure substance is an atom. Atoms are too small to study directly. Scientists make models of atoms to help picture them. Over the years, the model of the atom has changed because scientists have learned more and more about it. The model of the atom that scientists use today is called the electron cloud model. In the electron cloud model, the atom is divided into two main parts. These are the nucleus and the electron cloud. The nucleus is in the center of the atom and contains protons and neutrons. A proton is a particle that has a positive charge. A neutron is a particle that has no charge. The electron cloud surrounds the nucleus. It contains electrons and a lot of empty space. An electron is a particle that has a negative charge. Scientists have found other smaller particles. These particles make up protons and neutrons. Scientists are still learning more about these particles. History of the atom. The model of the atom has changed over the past 2,000 years. The first person to say that matter was made up of smaller particles was probably the Greek philosopher Leucippus. Democritus, a student of Leucippus, called the particles atomos, which means indivisible. Democritus believed that atoms were all hard solids in different shapes and sizes, but made of the same material. He also believed they could not be destroyed. Aristotle, another Greek philosopher, believed that matter could be divided again and again. Many people accepted Aristotle's ideas up until the 1600s. 5th century BC. Democritus proposed that all matter is made up of indestructible particles called atoms. 1803. John Dalton proposed that atoms are small solid spheres. His model of the atom looked like a billiard ball. 1897. Joseph John Thomson proposed the plum pudding model. In this model, atoms are positively charged spheres that have negatively charged particles embedded in them. In 1803, a British scientist named John Dalton used scientific methods to prove that atoms exist. Dalton developed an atomic theory that stated all matter is made of atoms, which cannot be created, divided, or destroyed. The chart below shows how the model of the atom has changed over time. Today, scientists generally agree that the electron cloud model is a good working model of the atom. As technology improves, scientists continue to learn more about the atom. 1911. Ernest Rutherford found that most of the mass of the atom is in its center. He called the center of the atom a nucleus. In his model, negatively charged electrons orbit a dense, positively charged nucleus. His model looks like a model of the solar system. 1913. Niels Bohr proposed that electrons travel in fixed orbits called shells. Electrons cannot move from one shell to another without gaining or losing energy. 1920s. Erwin Schrödinger and Werner Heisenberg proposed the electron cloud model of the atom. How are elements grouped? Elements. Look around you. Everything you see is made of tiny atoms. Most matter is made of more than one kind of atom. For example, water is made of hydrogen atoms and oxygen atoms. An element is a substance made up of only one kind of atom. Elements cannot be broken down into other substances, so they are also called pure substances. You are probably familiar with some elements such as carbon, aluminum, gold, silver, and copper. Gold is an element that is often used in jewelry. Silver and copper are elements that are used in jewelry and electrical wiring. About 100 elements are found naturally on Earth. They make up everything that has been found on Earth and in space. The 26 letters of the alphabet combine to form different words. Similarly, elements combine in different ways to make different types of matter. We identify each element by how many protons are found in its nucleus. No two elements have the same number of protons. For example, we know that any atom that has 79 protons in its nucleus is a gold atom. The atoms of elements have an even number of protons and electrons. If an element has 79 protons in its nucleus, there must be 79 electrons in its electron cloud. With the same number of protons and electrons, atoms have no electrical charge. Symbols for elements. Scientists use abbreviations for writing the names of the elements. These abbreviations are called chemical symbols, and they are made up of 1, 2, or 3 letters. A chemical symbol is usually the first letter of the element's name. Another letter from the name is added if that symbol is already used by another element. Some elements that were discovered in ancient times were given Greek or Latin names. The symbols for some of these elements were taken from their old name. For example, gold was given the symbol Au after its Latin name, aurum. When a new element is discovered, it's given a temporary 3-letter name. The name is based on the Latin name for the number of protons found in its nucleus. Silicon is an element that is used to make computer parts. Classifying elements. The properties of an element are determined by the number of protons and electrons in its atoms. Depending on its properties, each element is classified as a metal, a nonmetal, or a metalloid. Metals are elements that are usually hard, conduct heat and electricity well, and can be drawn into wires and hammered into sheets. Nonmetals are elements that are usually brittle, conduct heat and electricity poorly, and cannot be formed into wires or sheets. Metalloids are elements that have some properties of both metals and nonmetals. Neon is a nonmetal that is used in colorful signs. The periodic table. Scientists have organized all of the known elements in the periodic table. The periodic table lists the elements in order according to their atomic number. An element's atomic number is the number of protons in the nucleus of its atom. The elements are listed from left to right in order from the lowest atomic number to the highest. The metals are found on the left side of the table, and the nonmetals are found on the right side. Between the metals and nonmetals are the metalloids, which run in a zigzag line. Aluminum is an exception. Even though it is found along the zigzag line, aluminum is a metal. At the bottom of the periodic table are 2 rows of elements called the lanthanide series and the actinide series. The first element in the lanthanide series, lanthanum, has an atomic number of 57. It should follow barium, which has an atomic number of 56. Actinium, the first element in the actinide series, should follow radium. These rows were placed at the bottom of the table so that the table would not be too wide to fit on a page. Helium has 2 protons in its nucleus. It is a nonmetal. Information on the periodic table. You can find a great deal of information about the elements in the periodic table. Each element has its own individual block, which contains information about that element. Look at the block for the element chromium below. It shows the element's name, atomic number, and chemical symbol. It also tells that chromium is a metal and that it is a solid at room temperature. The word periodic means a regular, repeated pattern. The elements in the periodic table are organized in a pattern. Their properties change in a predictable way from left to right and from top to bottom. There are 18 columns in the periodic table. They are called groups or families. All the elements within a particular family react with other substances in similar ways. For example, all the elements in Group 1, except for hydrogen, react strongly with water. The elements in Group 18 react very little with other elements. These are called inactive elements. The 7 rows in the periodic table are called periods. The elements in a period have very different properties from one another. The first element of each period reacts violently. The last element of each period is always inactive. What are compounds and mixtures? Atoms together. Most atoms are found in nature as part of compounds rather than as elements. A compound is a substance made up of 2 or more elements that are chemically combined to form a new substance with different properties. Salt is a compound made of sodium and chlorine. Many substances in your body are compounds, including water, proteins, and DNA. Compounds are formed when elements combine in exact ratios. The properties of compounds are different from those of the elements that make them up. When sodium combines with chlorine, it forms sodium chloride, or table salt. When sodium combines with water, it reacts violently to form hydrogen gas and sodium hydroxide. Every particle of a compound is made of the same ratio of elements. For example, in table salt, there is 1 chlorine atom for every sodium atom. The properties of a compound are different from the properties of the elements that make it up. For example, sodium is a silvery white metal, and chlorine is a poisonous gas. These 2 elements combine to form a substance you eat every day, table salt. Chemical formulas. Every compound has its own chemical formula. It includes a chemical symbol for every element in the compound. It also includes subscripts that tell how many atoms of each element are in the compound. If there is no subscript beside a chemical symbol, there is only 1 atom of that element in the compound. For example, the chemical formula for water is H2O. This means water is made up of 2 hydrogen atoms and 1 oxygen atom. Mixtures. If matter is not an element or a compound, it is probably a mixture. A mixture is a combination of substances in which the atoms of the substances are not chemically combined. Mixtures may contain elements, compounds, or both. The substances in a mixture keep their own properties. The carrots, potatoes, and other vegetables that make up the bowl of soup below are all separate and easy to identify. Also, the components of a mixture may be present in any ratio. 1 bowl of soup may have more potatoes than another bowl. Separating mixtures. Mixtures can be separated easily. If you like, you can pick the carrots out of the soup and eat them first. To separate other types of mixtures, you need to know the physical properties of the substances that make them up. Suppose you wanted to separate a mixture of salt, iron fillings, and sand. The iron fillings are magnetic, so you could use a magnet to remove them. You could then add water to the salt and sand. The salt will dissolve, enabling you to filter out the sand using filter paper. Finally, you can evaporate the water from the mixture of water and salt so that only solid salt particles remain. Mixtures. Made of 2 or more substances. Do not have a symbol or formula. Can be separated by physical means. Compounds. Made of 2 or more elements. Have a chemical formula. Can be broken down into simpler substances. Elements. Made of only 1 kind of atom. Have a chemical symbol. Can't be divided into simpler substances. Solutions. When you look at a bowl of vegetable soup, you can see several different substances, but some mixtures look the same throughout. These are called solutions. A solution forms when one substance dissolves in another. Salt water is a common solution. The two components that make up a solution are the solute and the solvent. The solute is the substance that is dissolved. The solvent is the substance in which the solute is dissolved. In salt water, the solute is salt and the solvent is water. Whenever a solute dissolves in a solvent, the solute breaks down into very small particles and mixes evenly with the particles of the solvent. You can't see the salt particles in salt water because they are too small. Solids and gases also form solutions. Stainless steel is a solution of 3 solids, chromium, nickel, and iron. Kitchen utensils, such as forks, are made with stainless steel. Air is a solution made up of several gases. The main gases in air are nitrogen, oxygen, and argon. Yellow gold used in jewelry is a solution of gold and copper. Chromatography. Substances in a mixture can be identified based on how soluble they are. This can be done using a process called chromatography. In this example, the mixture of color pigments found in rose petals is being separated. As the liquid moves up the paper strip, particles of the pigments dissolved in the liquid form bands. Each band is a different pigment. Many police departments use chromatography to identify all kinds of substances. Concentration. Solutions may contain different amounts of solute and solvent. Concentration is the measure of the amount of solute dissolved in a solvent. A solution may be described as being either concentrated or dilute. A concentrated solution has more solute per volume of solvent than a dilute solution has. The white vinegar in your kitchen is a dilute solution of acetic acid and water. More concentrated acetic acid solutions are used in laboratories and food manufacturing facilities. Solubility is the maximum amount of solute that can be dissolved in a solvent at a certain temperature. We express solubility as grams of solute per millimeter of solvent. The amount of solute that can dissolve in a solvent is affected by the temperature of the solvent. For example, it is more difficult to dissolve sugar in iced tea than in hot tea. Adding the ice changes the tea's temperature. This affects the sugar's solubility in the tea. Whipped cream is a solution of a liquid and a gas. The liquid is butterfat and the gas is air. You can make a substance dissolve faster by mixing or stirring the solution. Increasing the temperature of the solvent or crushing the solute into smaller pieces also makes substances dissolve faster. Have you ever noticed that sugar sometimes falls to the bottom of a glass of iced tea? That's because the solution has reached its saturation point. This is the point at which no more solute can be dissolved in the solvent. All solutions have a saturation point, which limits how much solute can be dissolved in the solvent. Pressure also affects solubility. Carbon dioxide gas and flavored water form a solution when they're under pressure. When you open a soda bottle or can, the gas is no longer under pressure and is no longer soluble. The gas comes out of the solution, rises to the top of the container, and escapes into the atmosphere. Acids and bases. Many people think of acids as dangerous chemicals. Some acids can be strong enough to burn your skin, but many acids are weak. Some weak acids are found in foods that you eat, such as sour candy, pickles, milk, and citrus fruits. Weak acids in your body cells are important to your health. Because some acids are dangerous, never touch an acid to identify it. Instead, use an indicator, a compound that changes color when it comes in contact with an acid. Blue litmus paper is an indicator that turns red when acid touches it. Bases are commonly found in household products such as shampoo, oven cleaners, and drain cleaners. Strong bases are just as dangerous as strong acids. Many are poisonous and can burn your skin. Red litmus paper turns blue when dipped in a base. The pH scale. Scientists use the pH scale to describe the strength of acids and bases. The measurements of the pH scale range from 0 to 14. If a substance has a pH between 0 and 7, it is an acid. The strength of an acid decreases as pH increases. If a substance has a pH between 7 and 14, it is a base. The strength of a base increases as pH increases. A pH of 7 is neutral. Acids. Taste sour. Never taste a substance to test for the presence of acids. React strongly with some metals to form new compounds. Change blue litmus paper to red. Bases. Taste bitter. Never taste a substance to test for the presence of bases. Feel slippery. Change red litmus paper to blue.